Welcome to Product Embeddings and Similarity. Today we'll turn shopping baskets into a dense vector for each product, then use those vectors for similarity, recommendations, evaluation, and cold start fallbacks. Before we begin, let me briefly introduce today's guest speaker, Han Seojin, a research assistant in the MAVA lab. Seojin studied statistics and computer science, and in our lab she works on validating social video data pipelines, reviewing research designs, and checking whether the code actually does what the paper says it does. Around here, we sometimes joke that if Seojin doesn't pass it, it doesn't move forward. So she is the perfect person to guide us through a topic like product embeddings, where getting the logic, similarity, and evaluation right really matters. Seojin, thank you for joining us today.
Thank you, Dr. Lee. Hi, everyone. I'm Seojin from the MAVA lab. It's great to be here with you today. In this session, we'll look at how purchase behavior can be turned into product embeddings, and how those embeddings can help us measure similarity, make recommendations, evaluate performance, and think carefully about cold start problems. Let's get started. In this module, we'll learn product embeddings from purchase behavior and use them to compute item-to-item similarity and simple recommendations. If you've seen frequently bought together, customers also bought, or similar items, you've seen this idea in action. Instead of one-hot SKUs, we learn a dense vector per product, so products that appear in similar baskets end up close together, and that similarity can power cross-sell, bundles, and navigation. Here are the learning objectives for today. By the end, you should be able to take raw transaction data and convert it into basket-style training data, train an item to a VC style embedding model, and then query it for nearest neighbors. You'll also learn how to turn similarities into a recommendation list, and how to evaluate those recommendations with simple offline metrics like precision at K and recall at K. Finally, we'll talk about cold start, what happens when new products have little or no purchase history, and we'll implement a practical fallback strategy. Before we start, a quick note on deliverables. Throughout the notebook, we'll produce marketing-ready artifacts, a table of product vectors, a nearest neighbor table, an evaluation summary, and a 2D product map. Even if you never deploy a recommender, these outputs are useful for analysis and decision support. For example, the neighbor table can become a candidate list for customers also bought, and the 2D map can support catalog browsing or assortment review. Here's the agenda. We'll start with setup, then build intuition for product embeddings, load and standardize an Instacart-style dataset, and train embeddings using a Word 2vec style model. After that, we'll explore item-to-item similarity, build a couple of simple basket-based recommendation heuristics, visualize products in 2D, run a minimal offline evaluation, and finally address cold start and marketing use cases. One more important thing, interpretation rules. First, nearest neighbors are candidates, not truth. A model can suggest that two items belong together, but it does not prove the relationship is causal or profitable. Second, 2D maps are for exploration. Dimensionality reduction methods distort distances, so we use them to spot clusters and navigate, not to tell stories about the axes. Third, offline evaluation is diagnostic. Precision and recall at K help compare methods, but they do not replace an online experiment. And finally, cold start is structural. Many real catalogs have long-tail items with sparse history, so we always need a fallback mindset. In this first code cell, we install and import the libraries we need: Pandas, NumPy for data, Gensim for Word 2vec, and scikit-learn for evaluation and dimensionality reduction. We also set a global random seed, 42, for reproducibility. This notebook is designed to run on CPU in Colab because we sample the data for speed. Next, we set up the project folder structure, where data lives, where outputs go, and where we can save models and figures. We also turn on a fast mode. This is a practical choice for a video-friendly Colab run. We'll work on a subset of the data so we can iterate quickly. If you want maximum fidelity, you can turn fast mode off later, but be aware that the full Instacart prior table is very large and can exceed Colab memory if you load it naively. This utility cell creates a few helper functions. The timer function gives us simple runtime feedback, so we can see which steps are slow. The save function writes tables to CSV or Parquet, so the outputs are easy to reuse outside the notebook. And we enable progress bars for Panda's operations. Nothing conceptual changes here. It's just tooling to keep the rest of the notebook clean and easier to follow. Part 1 is all about managerial intuition. We want to understand what product embeddings represent, why they're useful in marketing, and what we should and should not claim from them. As we go, keep the key framing in mind. Embeddings are a compact representation of behavior patterns. They help us generate candidate insights at scale, but they still need business validation. Let's start with the marketing problem. In large catalogs, manual relationship mapping doesn't scale. You might have tens of thousands of SKUs. Most customers buy only a tiny fraction, and the catalog changes constantly. So the core questions become, what items are credible cross-sell candidates? Which products look like substitutes versus complements? And how can we help customers browse similar items even when they don't have the right search keywords? Product embeddings are one way to answer these questions automatically by learning relationships directly from purchase behavior. Here's the NLP analogy that makes embeddings intuitive. In NLP, Word2Vec learns that a word is defined by the context it appears in. We can reuse the same idea in commerce. A product is defined by the other products it appears with, either in the same basket or close together in a user's timeline. So, words become products, sentences become baskets or sequences, and the context window becomes a co-purchase neighborhood. If two products appear in similar contexts, their vectors should end up close in the embedding space. There are two main behavioral signals we can learn from. First is basket-based co-purchase, items bought in the same order. This is great for frequently bought together or cross-sell style insights. Second is sequence-based co-occurrence, items that show up near each other over time for a given user. This can capture transitions, like replenishment cycles or evolving intent. In this notebook, we train basket first for clarity and speed, and we treat sequence-based training as an optional extension. Now, what does similarity mean here? Operationally, we use cosine similarity between embedding vectors. Cosine similarity focuses on the angle between vectors, so it captures whether two products point in a similar direction in the learned space. A high similarity score often suggests either substitution, two items playing the same role, or complementarity, two items frequently appearing in the same shopping mission. But there are pitfalls. Popular items can become neighbors of everything, and behavioral similarity can produce some surprising results that don't sound semantically similar. That's why later we'll also look at coverage, and we'll keep emphasizing that these are candidate insights, not final decisions. In Part 2, we shift from intuition to data. Our goal is to load the dataset and standardize it into a minimal transaction log that we can reuse consistently for training, similarity, and evaluation. The main output is DFF-TX, one row per product in order, with user ID, order number, add to cart order, and product ID. We also build a product lookup table to translate IDs into readable names. This notebook expects an Instacart-style file layout: orders, order products prior, and products. The important point is not Instacart specifically. It's the structure. We need order-level product lists, and we need a mapping from product ID to product name so we can interpret results. If the files are missing, the notebook can fall back to a tiny demo dataset, so the pipeline still runs end-to-end. This cell handles dataset availability in a simple way. If the Instacart CSVs are not found locally, we download a zip bundle from Dropbox and unzip it into the expected folder structure. A key detail is the Dropbox parameter, DL-1, which forces a direct file download instead of an HTML preview page. Once extraction is done, the required CSVs should exist under the raw data folder, and the notebook will automatically switch into Instacart mode. The next helper cell is about memory safety. The Instacart prior table can be huge, so instead of reading it all at once, we define chunked CSV readers. We stream the file in manageable pieces, filter to the subset of orders we care about, and then concatenate only what we keep. This pattern, stream, filter, then combine, is a common workflow in applied ML when your raw logs are bigger than memory. Now we actually load the data and standardize it. First, we load the small tables, orders and products. Then, because fast mode is on, we sample a subset of users and keep only their orders. In this run, we keep 5,000 users, which corresponds to about 77,862 orders. Next, we streamload the prior table and keep only the rows for those orders. The filtered prior table ends up with 778,814 product and order rows. Finally, we merge to build DFTX. The key result here is the shape. DFTX has 778,814 rows and 5 columns, and the product lookup has 49,688 products with names. This standardized format is what every downstream step will rely on. This sanity check cell is a quick, does it look right? Moment. We print the number of unique users, orders, and products in our working sample. In this run, we have 5,000 users, 77,162 orders, and 28,966 products appearing in the transaction subset. Then we preview a few rows of DFTX and also a version joined with product names. Conceptually, what you want to see is that each order ID has multiple product IDs, and the add to cart order gives you a stable within order sequence if you want it. Let's summarize part 2. We now have a clean transaction log, DFTX, and a product lookup table for interpretation. From here on out, our job is to convert DFTX into training corpora for embeddings, basically lists of product tokens, and then train a model that learns vectors from co-occurrence. Part 3 is where we actually train embeddings. We will convert DFIX into a basket corpus, one list of product tokens per order, and then train a Word2Vec model on that corpus. If you've seen Word2Vec in text, this is the same algorithmic idea, just applied to products instead of words. The output is a trained embedding model, plus a tidy table of vectors we can use for similarity, maps, and evaluation. Before we code, let's clarify the design choices. An order is conceptually an unordered set. Customers don't necessarily add items in a meaningful semantic sequence, so we treat each basket as a context container. To avoid accidentally baking and ordering artifacts, we can shuffle tokens inside each basket across training epochs. We also apply a minimum frequency threshold, so extremely rare items don't inject noise or instability into the model. These are practical classroom decisions. They make training faster, more stable, and easier to interpret. This settings cell defines the main hyperparameters for embedding training. The key ones are the minimum item frequency threshold, the embedding dimension, the context window size, and the number of training epochs. In this run, we keep items that appear at least 10 times, we learn 64-dimensional vectors, we use a window of 8, and we train for 10 epochs. Think of these as reasonable defaults, not magic numbers. Now we build the basket corpus. We start by converting product ID into string tokens, because the embedding model expects tokens as keys. Then we count frequencies and keep only the items meeting the minimum frequency threshold. In this run, we start with 28,966 unique items in the sampled transaction log, and after filtering, we keep 9,692 items for training. Next, we group by order IID to produce one basket per order. A useful diagnostic is the basket size distribution. Here, after filtering, the average basket has about 9.8 items. Half of the baskets have 8 items or fewer, and the 90th percentile is 19 items. So we're learning from realistic shopping baskets, not just tiny toy examples. This is the embedding training step. We train a Word2Vec model using skipgram with negative sampling, often abbreviated as SGNS. Skipgram means we learn to predict context items from a center item, and negative sampling means we train against a small set of noise items to make training efficient. Here we treat each basket like a sentence, and the window size controls how broadly we consider items as being in the same context. Because baskets are not truly ordered, we shuffle items within each basket across epochs. After training, the model vocabulary size is 9,872 items, which matches the number of products we kept after frequency filtering. Now we extract the learned vectors into a tidy table. We take every token in the embedding vocabulary, pull its 64-dimensional vector, and combine it with the readable product name. That's why the vector table has 9,672 rows and 67 columns. Token, name, product ID, plus V0 through V63. This table is convenient because it separates the model from the analysis. Once you have DEF vectors, you can compute similarity, build maps, cluster products, or join to other marketing data without rerunning Word2Vec. Quick recap for Part 3. We've transformed transactions into a basket corpus, trained a basket-first embedding model, and extracted a clean table of vectors. Now we can finally do what embeddings are good at: retrieve nearest neighbors and turn similarity into recommendations. Part 4 is where embeddings turn into something actionable. First, we'll do item-to-item similarity. Given one product, retrieve its closest neighbors in the embedding space. Second, we'll build a simple basket-to-recommendation prototype. Given items already in a cart, propose additional items. We'll keep the functions simple and reusable, because we'll use the same recommendation logic again in offline evaluation. This helper cell builds the lookup dictionaries and functions we'll use throughout Part 4. We create mappings between product IDs, tokens, and names, and we define two key utilities: a search function that helps you find product IDs by keyword, and a most similar function that returns the top n neighbors for a given product. Conceptually, this is the interface between the embedding model and our marketing questions. It makes it easy to ask, what is similar to this SKU, without manually handling tokens. Here's a quick demo of the search helper. We search for products containing the word milk in their names. The output is simply a short list of matching products with their IDs. This is handy because many analyses start with a human idea, like, let's look at milk, and we need the correct product ID to query the embedding model reliably. Now we query nearest neighbors for product ID 24852, which is banana. The table shows the closest items and their cosine similarity scores. In our run, banana is close to other produce such as large grapefruit and Honeycrisp apple, a 0.74, large lemon and cucumber Kirby, DAR 0.70, which makes intuitive sense. But we also see surprising neighbors like zero-calorie grape soda and almond breeze almond milk. That's the key lesson. Embeddings capture behavioral similarity, not taxonomy. If the same shopper segment buys these together, the vectors move closer. This cell repeats the neighbor search for several anchor products, so we can build intuition. In our run, we look at popular anchors like banana, bag of organic bananas, organic strawberries, organic baby spinach, and organic Hass avocado. Notice how the model often pulls neighbors from related shopping missions: fresh produce, healthy staples, and frequently co-purchased items. Also notice that a few neighbors may feel odd, like a beverage showing up near fruit. That's a great reminder. Embeddings reflect co-occurrence patterns in the data sample we trained on, including whatever customer segments and shopping missions are present. Now let's move from similarity to recommendation. We'll implement two lightweight strategies. Method A is neighbor voting. For each item already in the basket, we grab its neighbors and add up similarity scores. The candidates that score high across multiple basket items rise to the top. Method B is basket mean. We treat the basket as a single point by averaging its vectors, and then we retrieve items closest to that average. Both are simple, but they capture two different intuitions: vote across items versus summarize the basket's overall theme. This code cell implements both recommendation methods. The first step is cleaning the basket. We remove duplicates and drop any items that aren't in the embedding vocabulary. Then we define neighbor sum and basket mean. Neighbor before sum is easy to explain in marketing terms. It finds candidates that are compatible with multiple items already in the cart. Basket mean treats the cart like a profile vector and recommends items similar to that profile. These are not production-grade recommenders, but they're strong baselines and very useful for intuition. Now we test two basket-level recommenders on a few sampled orders: neighbor voting and basket mean. In the first basket, pure water, cola soda, Coke Classic, lemon lime soda, and sparkling waters, neighbor voting recommends more sparkling water variants like sparkling waterberry and lime sparkling water. That's a clean cart page cross-sell. Basket mean is often more theme-based and can surface adjacent items that co-occur with the overall basket pattern. We'll judge which behavior is better in Part 6 with offline evaluation, because intuition doesn't scale to thousands of items. Recap for Part 4. We can now query nearest neighbors for any product, and we can turn a basket into a ranked list of candidate recommendations. Next, we'll zoom out and visualize the catalog in 2D, which helps build intuition about clusters and product neighborhoods. Part 5 is a 2D product map. The goal is not to prove anything, but to create a visual tool for exploration: clusters, neighborhoods, and navigation. We'll take the 64-dimensional product vectors and project them into 2 dimensions using a dimensionality reduction method. PCA is fast and stable, and UMAP often shows nicer local structure, but can be heavier. Even though we're doing this inside Colab, the exact same idea is used in many product teams for interactive catalog exploration. In this settings cell, we prepare the matrix for dimensionality reduction. X is our embedding matrix, 1 row per product in the embedding vocabulary, and 1 column per embedding dimension. In this run, X has shape 9,672 by 64. We also choose a reduction method. Here we use PCA, and we normalize vectors first. Normalization matters because cosine similarity is our main notion of similarity, and normalizing aligns PCA more closely with cosine-based geometry. Now we actually compute the 2D projection. With PCA, we're finding the 2 directions that capture the most variance in the embedding vectors. In this run, the first 2 components explain about 23.9% of the variance, which is normal for high-dimensional behavioral embeddings. The output is DEF map 2D. For each product, we now have an X and Y coordinate in 2D space. This is the foundation for our scatter plot, and also for map-based navigation later. This cell plots a 2D product map using dimensionality reduction. Use it for exploration and navigation, clusters and neighborhoods, not for precise ranking because 2D distances are approximate. Right after this, we'll do an optional TensorFlow embedding projector mini-lab for interactive exploration. Now, we'll export the learned vectors and explore them interactively in the TensorFlow embedding projector. After running this code, you will be asked to download 2 files for the TensorFlow embedding projector. Then open the embedding projector in your browser, click Load Oscur, and upload e6 embeddings.tsv, vectors, and products.tsv labels. Search for an item like banana and explore its neighborhood. Remember, the 2D view is approximate. Use projector for intuition and cosine similarity for precise ranking. Part 6 is minimal offline evaluation. We'll use a lightweight hide one item protocol. For each basket, we randomly hold out 1 product as the target and treat the remaining items as context. Then we generate a top K list from the context and check whether the target appears in that list. We'll compare our 2 embedding-based methods, neighbor voting and basket mean, against a simple popularity baseline. And we'll compute catalog coverage at K, which tells us how broad or narrow the recommendation experience is. This cell sets the evaluation parameters. We choose the K values we want to evaluate. Here, 5, 10, and 20. And we choose how many evaluation cases to sample. In this run, we evaluate 2,000 cases, which is enough for a quick diagnostic without making the notebook too slow. We also set how many per-item neighbors to consider for the neighbor voting method. That parameter controls the candidate pool size before ranking. Now we build the evaluation cases. We iterate over orders, convert each order into a cleaned list of in-vocabulary tokens, and keep only baskets with at least 2 valid items. Then we randomly select 1 item as the target and treat the rest as context. In our run, we have 72,943 candidate baskets after filtering, and we sampled 2,000 of them for evaluation. The printed example shows a context basket of size 32 with a target item like organic Fuji apple. This step is important because evaluation quality depends on having a realistic context target split. This helper cell defines fast recommenders that return just token lists. The logic is the same as our earlier recommendation functions, but here we avoid data frame overhead, so evaluation runs faster. We implement 3 methods: neighbor, sum, basket, mean, and a popularity baseline that always recommends the most frequent items. This setup makes the comparison fair. Each method produces a top K list, and we score them using the same rules. Now we run a minimal offline evaluation. Because we hide exactly 1 target item, recall at K equals hit rate at K here, the fraction of cases where the hidden item appears in the top K list. Neighbor voting, neighbor sum, is best. Hit rate is nek smart year 30% hor at K5 and wien not 12% at K year 20, beating basket mean 5.40% and 9.65%. Popularity can look competitive on hit rate, but it's Coverage is tiny. It recommends almost the same few items to everyone. So look at accuracy and coverage. Neighbor, some covers about 64% of the vocabulary at K20, while popularity coverage is near 0. Recap for Part 6. We now have a quick offline view of quality and breadth. Neighbor voting is stronger in this run, and both embedding-based methods cover far more of the catalog than a popularity-only approach. Next, we address cold start. What happens when products are missing or too sparse to learn reliable behavior embeddings? Part 7 is about cold start. Behavior-only embeddings work best when an item has enough interaction history to learn stable co-occurrence patterns. But in real catalogs, many products are new, seasonal, or long-tail, and they may not appear often enough. Here we focus on new item or sparse history cold start. The idea is simple. If the item is not represented well in behavior embeddings, we need another signal to generate candidates. This matters a lot operationally. If you ignore cold start, recommendations become overly concentrated on popular items, and new product launches get buried. From a marketing perspective, that reduces exploration and limits your ability to promote new SKUs. So even a simple fallback is valuable. It keeps the system usable across the full catalog, not just the head items. This cell quantifies cold start. We have 49,688 products in the full catalog, but only 9,672 in the embedding vocabulary. So over 80% of items have no behavior-based vector in this setup. That's why cold start fallback is not optional in real marketing workflows. New and long-tail products are exactly where recommendations often matter most. For cold start, we fall back to content similarity using product names. We build TF-IDF vectors for product name and use cosine similarity. For example, out of vocabulary, all seasons salt retrieves neighbors like Four Seasons peppercorns and Nature's Seasons seasoning blend. Content similarity is available immediately, but it's based on text overlap. Behavioral similarity reflects how customers actually use products. In practice, combining both signals is the goal. This cell wraps the logic into a simple hybrid recommender: embeddings when available, TF-IDF when not, and popularity as a last resort. The key takeaway is operational. You still produce reasonable candidates even when the basket includes new or sparse products. Recap for Part 7. We've seen that behavior-only embeddings leave many products out of vocabulary, especially in the long tail. We added a minimal content-based fallback so we can still generate candidates for new or sparse items. Now we'll wrap up by translating embeddings into concrete marketing outputs: cross-sell candidates, bundle ideas, redundancy signals, and catalog navigation helpers. Part 8 is where we translate the technical outputs into marketing actions. We'll build small, readable tables that could realistically be used in a product team meeting. Cross-sell candidate lists, bundle brainstorming ideas, redundancy signals for assortment decisions, and navigation helpers for browsing similar items. The goal is not to build a perfect recommender today, it's to connect embeddings to practical marketing workflows. Here are the key use cases to keep in mind. Cross-sell, customers also bought candidates on the product page or in the cart. Bundling, small sets of items that naturally go together, useful for promotion brainstorming. Assortment redundancy, extremely similar items can indicate overlap, line extensions, or cannibalization risk. Catalog navigation, similar items, browsing when search queries are weak. Now let's generate compact tables that operationalize these ideas. This first use case cell selects a set of anchor products. We pick the top N most frequent items in our transaction sample. Here, the top 10, and we keep both the token and the readable name. In our run, the anchors are familiar Instacart staples like banana and other high-frequency produce items. Anchors are just a practical starting point. In a real project, you would choose anchors based on business goals, like key categories, promoted items, or strategic brands. Now we generate cross-sell candidates for each anchor. For every anchor product, we retrieve its nearest neighbors in the embedding space and store the similarity scores. For example, bag of organic bananas has neighbors like organic strawberries and organic baby spinach with high similarity, very plausible cross-sell candidates. In practice, this table is exactly what you would feed into a "you may also like" component, subject to business rules like inventory, margin, and category diversity. This cell creates simple bundle ideas. For a handful of seed items, we take the top embedding neighbors and assemble a small bundle, seed plus a couple of candidates. For example, banana pairs with other fruit items in our run, which makes sense as a fresh produce-themed bundle. Think of this as a brainstorming tool. Real bundle optimization would also consider price, margin, and whether the items are complements versus substitutes. Next, we create a redundancy signal for assortment decisions. We take a set of popular items, find their strongest neighbor relationships, and then look for pairs with extremely high similarity. High similarity pairs can suggest overlap. Maybe two products serve the same role, or one is a close alternative to the other. This doesn't mean you should remove a SKU, but it's a useful flag for category managers. These items live very close together in customer behavior. Let's review positioning and differentiation. Finally, we use the 2D map for navigation. Once we have X and Y coordinates for each product, we can define neighbors as points that are close in the 2D space. This gives you a simple way to build a catalog browsing experience. Click an item and show nearby items on the map. The output here shows, for an anchor like banana, which products are closest in 2D distance. Just remember, 2D distance is an approximation. It's great for exploration, but for precise similarity ranking, the original embedding cosine similarity is usually more reliable. Let's wrap up. We trained product embeddings from baskets, queried item-to-item similarity, built simple recommenders, evaluated them with precision, recall, coverage, and handled cold start with a content-based fallback. We also turned the outputs into marketing artifacts, cross-sell candidates, bundle ideas, redundancy flags, and navigation helpers. Thank you for watching, and very nice to meet you all. See you in the next topic.